Briefly, we have a trapezoidal approximation graph for y equals 3 plus x squared on the interval from x on the x interval from 0 to 2, moving by increment 0.5. Moving by increment 0.5 means that we start at x equals 0 and we move 0.5 units until we get up to x equals 2. So the x values are as you see them, and the corresponding y values we can easily confirm by plugging these values in for x to give you the y values. You're going to get these y values. This is going to lead us to the trapezoidal graph. And when we first draw the graph, we just label our points 0 through 2 on the x-axis. We label our widths 0.5, and we label our graph altitudes, and we draw the slope segments. Then maybe we go to a table. Maybe we can do these in our head, depends on the situation. We do a table where we have x and y values, and it's useful to calculate the rise, the run, and then the slope. The rise being from 3 to 3.25, the rise is 0.25. From 3.25 to 4, we're going up by 0.75. We get this rise, and so forth. So we get the rises. The run is always 0.5. For any of these segments, the run has to be 0.5 because that's the width of each trapezoid. That's the difference in the x coordinates. So we get these rises, these runs, and we very easily and quickly calculate our slopes. Then we get our average altitudes. The average altitude of each trapezoid is the average of its left and right altitudes. So for the first trapezoid, we average 3 and 3.25. Gives us 3.125, which we might well round off depending on the situation. And we do the same for all the trapezoids. And you can again and should confirm these average altitudes. We then multiply the average altitude by the width, because if we cut the trapezoid at the midpoint, its altitude will be, at that point, will be the average altitude. We'll get a little triangle here that we can flip over to form a rectangle whose dimensions are width and by the average altitude. So we multiply those and we get our areas. And then each area is added to the accumulated area of the preceding, meaning that we accumulate areas from the left-hand point of the graph. By the time we get to the 0.5 to the end of the first trapezoid, we will have accumulated area 1.56, just matching the area of the first trapezoid. By the time we get to the end of the second trapezoid, we'll have accumulated 1.81 more units of area, which will be added to the area we had accumulated through the end of that trapezoid. Now we get to the end of the third trapezoid, we add the 2.31 units of area gained and with the third trapezoid to the area accumulated through the end of the second, and we get the accumulated area through the third, and then similarly through the fourth. So the accumulated area always represents the total area accumulated through the right-hand end of the trapezoid. Now, when we make this approximation, straight line approximations at the top of each trapezoid, we know that this graph gives us a parabolic curve, a nice smooth curve that's going to dip down below the approximating segment for each trapezoid due to the nature of its concavity. And it's only going to match the approximating segment at the left and right hand end of each trapezoid. So it's going to actually dip down below our trapezoidal approximation so that the actual area under the curve is going to be, in my estimate, was 1 or 2%. Turned out that was a good estimate, but that was just dumb luck. 1 or 2% less in this case than the areas we get when we do the trapezoidal approximation. And we make the calculus connection now. And calculus, the derivative of our function, and assuming you know the calculus, if you don't, you want to still understand that this interpretation is kind of central to the meaning of the calculus. Okay, so that when you do get to calculus, you can come back and refer to this. In other words, in any case, in calculus, we find that the derivative is very easy to calculate. There's just a very simple rule for calculating the derivative, and we represent that as y prime, y with an apostrophe read y prime equals 2x. And anybody who's had calculus can figure that out. Antiderivative, the simplest antiderivative of this function, there are infinitely many, is x cubed over 3 plus 3x. And we could add any constant number, which is why I say there's infinitely many, but we don't add the constant. And I don't want to get too deep into that. Now, the values of y prime equal to 2x are easy to calculate for x equals 0 through 2, and we get these values. And the value of this big capital fancy y here that represents our antiderivative are easy to calculate. We just plug the x coordinates into this expression and this expression. We get this column of numbers, this column of numbers. Okay, well, this column of numbers, if we want to get the number that corresponds to the first trapezoid, we're going to average the first and second values, and we get 0.5. Okay, so the average value of y prime in the first trapezoid is 0.5. On the second, we average 2 and 3 to get 1.5. On the third, we average 3 and 4 to get 2.5. And I didn't go down, actually I kind of did go down to the last trapezoid. Yeah, I didn't. Okay, I'm going to correct something there. I kind of messed up my spacing here. I didn't have the one, I had the 1.5, but I had it here, and I had the 2.5 here. Obviously, the average of 1 and 2 is 1.5. The average of 2 and 3 is 2.5. 3 and 4 is 3.5. Okay, these average values corresponding to the four trapezoids correspond exactly to our slopes. So our average value of our derivative is the slope on each of these. Now that isn't always the case with every possible function. For a quadratic function, which this is, it will always be the case. If it isn't the case, we still get a good approximation when we average the values of y prime. The values of our big fancy y corresponding to the antiderivative function are very easily calculated, and we see that these are very close to the values of the average altitude. So that the average altitudes, in a sense, represent the values of our antiderivative function, and the average values of y prime, the actual derivative function, are represented, or at least closely approximated, by the values of our slope. Very important. Now we back off the calculus for a minute. Specific interpretations of our graphs. If we have a graph of velocity in meters per second versus clock time in seconds, we interpret the graph altitude, average altitude, slopes, the areas, and the accumulated areas. It's very easy to do this interpretation once you get used to it and once you know what the quantities actually mean. Our velocities are our graph altitudes, and we list them here, and they occur at these clock times, and you can look back at the graph and see why that is. Our average velocities, well, we average the two velocities that correspond to each trapezoid, and we get these average velocities. So we have these average velocities occurring on our consecutive half-second intervals. So we have 1, 2, 3, 4 intervals corresponding to 1, 2, 3, 4 trapezoids with these average altitudes. Average rate of change of velocity with respect to clock time, that's going to be the interpretation of the slope. Okay, the slope is going to represent rise, change in velocity, divided by run, change in clock time, and that's going to give us the slope. And the units are going to be meters per second velocity change divided by seconds of run or width of the trapezoid, and we get these values indicating the average rates of change of velocity with respect to clock time, a concept that you might not really be all that comfortable with, but that's what we get. Okay, and the units will be meters per second divided by seconds, or meters per second squared, again on consecutive intervals. Changes in position, well, our areas are going to give us change in position because the area represents average graph altitude, which represents average velocity in meters per second multiplied by width in seconds gives us change in position. Okay, and we get these results that the object will change position by approximately each of these amounts on each of the corresponding intervals. Okay, and then our positions relative to the t equals 0 position will be the accumulated areas, because for each new trapezoid we add the change in position corresponding to that trapezoid to the accumulated change in position up to the beginning of that trapezoid, and we get the change in position through the end of the trapezoid, from the initial instant through the end of the given trapezoid. If the interpretation, or if the graph represents force in newtons versus position in meters, we interpret the same quantities. Our graph altitudes represent our forces. Our average altitudes represent our average forces. Our average rate of change of force with respect to position, well, that's what we get if we look at the slope, because a slope is a rise, which is a change in position or change in force, divided by a run, which is a change in position. Dividing change in force by newtons by change in position, which is in meters, we get these average rates of change of the force. Pulling something apart, it's the average rate at which it's getting harder and harder to pull them. Okay, work done. Now that's an interpretation we did previously. I'm not going to go into the details of that, but when we multiply the average altitude by the width to get the area, we're multiplying the average force by the change in position. And that gives us work for reasons that you probably aren't completely comfortable with at this point. But we understand the units are newtons, the units of our average altitude, times meters, the units of our width, and these are the results, and that does correspond to work done or energy expended. And then work relative to the initial position or energy expended relative to the initial position. We just add up the work on the first interval to the work on the second. We get the accumulated work for the first and second. Add the work done on the third interval. We get the accumulated work through the end of the third interval. Add the work in the fourth interval. We get the accumulated work through the end of the fourth interval. Accumulated work or energy expended. So I make a note here. This also represents the cumulative energy expended through the end of each trapezoid. This much, so many newton meters through the end of the first, from the beginning through the end of the second, this much energy expended, etc. You can again review interpretation of force versus position trapezoid to understand that maybe a little better, but that'll come along later in the course.